Okay, we are starting Unit 2, and Unit 2 is all about reactions in solution. When I say in solution, what do you think I'm talking about? In what? Yeah, in water. So water is going to be a big focus this unit, and how substances behave in water is something we're really going to look at. All right, so here we have a picture of water. You can see that water is attempting to dissolve this plus-minus ion lattice. What kind of substance would this plus or minus ion thing be? What kind of compound? Yes, this is definitely an ionic compound. So when water dissolves a soluble ionic compound, not all ionic compounds dissolve, it is going to try to sneak its way in, and it can separate those ions strictly because of water's polarity. If you look at that little picture on your notes, water, again, we've kind of already talked about this, all the electrons are pulled toward the more electronegative oxygen, making this side of water partially, that lowercase delta means partially negative, and this side of water partially positive. So water will orient itself around these ions as it kind of separates them from the lattice, and the term is solvate. It's going to solvate the ions in the appropriate way, in the appropriate direction. So if you look here at this anion, whoa, I didn't mean to do that. If we look here at this anion, this negative ion is surrounded by water, and the water is oriented where the positive side of it is electrostatically attracted to the negative ion. And so that attraction between the two is not a bond. It's an electrostatic attraction, just like magnets. Okay? Sort of like magnets, not exactly like magnets. But here is a positive ion, and look at the change in the orientation. You see how the water molecules now are facing it the other way? That partially negative is facing it. That's the level of detail you might be expected to do when we're asking you to solvate ions or to draw dissolving. Okay? So let's go a little bit into the concept of dissolving. So does anyone know what an electrolyte is? Don't say Gatorade. Gatorade is an example of an electrolyte. But what's the definition of it? Something is an electrolyte when a salt is an example of electrolyte, still not a definition, yeah. Exactly. When this substance is dissolved, an electrical current can pass through solution. That's what an electrolyte is. So, and that's true because in order for electrons to move through solution, there has to be free-flowing ions, so charge can go from place to place to place. All right? So here, this is an example. This first thing is an example of a strong electrolyte. A strong electrolyte, we say, is the substance that 100% ionizes or dissociates. Or ionizes. People, I'm not the kind of person to freak out between the differences in those two words. So here, if you see in the picture, everything's an ion, right? So what substances are in that class of things? What are some things that dissociate or ionize 100%? Okay, salt, more specifically, soluble salts. Okay. Tomorrow we're going to go over solubility rules, so soluble rules. This is what happens when I try to talk and write. Soluble salts. Soluble salts are things that are strong electrolytes. Something else you talked about, we said, oh, this dissociates 100%, but these things don't. Say that louder, I can't. Well, you have to be ionic. Covalent doesn't, so hang on to that. That's going to fall into one of these categories. There was something else you learned. Matt. Yes, perfect. Strong acids. Good job. Strong acids or bases dissociate 100%. Okay? So those are examples of things that when we run an electric current through it, and we're going to see this little apparatus on Wednesday, if it gets here in time. I just ordered it last night. You'll be able to see it will light up really bright if we've got a strong electrolyte in there. Next up is a weak electrolyte. Look in here, we have very few ions. Most of the stuff is undissociated. So what falls into this category, do you think? Yep, weak acids and bases. That's going to be our primary component of these, weak acids and bases. Now, what you also might get here are some slightly soluble salts. And that will depend on the level of amount they do dissolve. You're going to learn the solubility rules, and you're going to say this is soluble and this is insoluble. Insoluble things actually do dissociate to a minor percentage, depending upon it's something called its KSP, which we will learn this year. But I'm not too concerned about you knowing about this. This could fall either in that category or that category, depending upon the level it does dissolve. And the last one here are things that dissolve in water but don't ionize. Can anyone give me a real-life example of something that dissolves in water but doesn't split into ions? Falls into that category you said. How about sugar? Does sugar dissolve in water? Yeah, so like C6H12O6, it dissolves in water because it's polar, so these things have to be polar. So it too has a partially positive and partially negative end. So maybe this end is negative and this end is positive, and the water will kind of, half of it will surround one way, the water will flip and surround it the other way. So we can still get dissolving with things that are polar, but they don't break up into ions, so we can't run electrons through this, so this light bulb won't turn on at all. All right, and again, we're going to actually see this in action on Wednesday. Questions on this? All right, so now we're going to do a little bit of a categorization of strong and weak acids and bases, and then apply it to some equations, that reactions we're going to write. On the side here, I'm going to make a note and review our rules for strong acids and bases, how to categorize them. Strong acids, let's do that first. Okay, binary acids. There are the ones with just our single elements in it, right? Does anybody remember the strong binary acids? I bring clay, correct. So remember I bring clay for our new house? I bring clay, stop. Those are the strong binary acids. Good. Now, ternary acids, we had a long rule for strong ternary acids. I'm going to start it off. If we have two or more, who remembers? O's and H's, it is strong. All right, so that means HNO2 versus HNO3. HNO2, does it have two more O's and H's? Nope, so that's weak. Does HNO3 have two more O's and H's? And it's two or more O's and H's, okay? So yeah, this one is strong. I should write strong. I don't want you to think that means solid. It means strong. Now, there's a rule that supersedes all these rules, and that's any acid containing a carbon. What are those? Yep. And by carbon, I mean, when I say C, I mean carbon. HCl, I had students think it was weak because it had a C in the name. That's not a carbon. That's a chlorine, okay? So it has to have a carbon in it. Any acid, so you don't even look at the O's, because you would potentially, in these organic acids, there's going to be a lot of more O's than H's, but they're organic acids, and by definition, those are weak acids. Okay? All right, let's do our bases. Let's see if I can be fancy and change some color action here. Maybe not. Maybe it's not going to play ball. That's too much work. All right, bases. Does anybody remember the strong bases? Bases are usually hydroxides. Take a guess. Oh, I forgot about the B. Yeah, I didn't tell this to the last period. It's a B on the periodic table. So if we go down, imagine rubidium, strontium, cesium, and barium being the base, like the base of the B, and then go up to lithium as the stem. So the B goes from lithium down and there. Okay, so it's group 1 hydroxides. Well, no, because we don't even deal with that because it's radioactive and it would be gone before we could even deal with it. So we don't even talk about those guys. So group 1 hydroxides and barium and strontium hydroxide. And it makes a B on the periodic table. Forgot about that last period. Okay. Any other hydroxide is going to be weak. Calcium's on the edge. Calcium can go either way, and we'll talk about that. It depends on the concentration. If it's like highly concentrated, it doesn't all dissolve, so we consider it weak. If it's dilute, it'll all dissolve, so we say it's strong. But on the AP, they'll go either way with that one. Ammonia, though, is our best example of what kind of base? Strong or weak? Weak. This is the consummate example of a weak base. You might not think much of ammonia now, but by the end of AP Chemistry, you're going to be so sick of ammonia because we use it all the time in all sorts of equation writing. It is the most popular base, weak base example that we have. All right, so what we're going to do here, we're going to list whether each of the following is a strong electrolyte, a weak electrolyte, or a non-electrolyte. And if it's strong, we're going to write a dissociation equation. If it's weak, we're going to write an equilibrium equation because, and I'll explain it when I get to one, because things that are weak do dissociate a little bit, so there is some reaction with water going on, just not a lot. And we'll get to that. But let's start with this first one, HClO4. What kind of electrolyte is that? Strong. Why is it a strong electrolyte? Because it's a strong acid. So it's strong. This is going to dissociate in water. There's two ways you can write dissociation equations. We could sit there and just take it like this, and we draw a single-headed arrow in the right direction. 100% of this turns into these two ions. This is where you have to know your polyatomics. Don't be splitting up ClO4 into separate things. Polyatomic ions are covalently bound within them. The ionic bond exists from the electrostatic attraction between the H plus and the ClO4 minus. Okay? That's where the dissociation happens. Another thing you can do, and this is what we're going to do more commonly when we get to acids and bases, is the fact that the true thing that's happening is it's reacting with water. When something dissociates, we actually get that water, again, sneaking in and solvating the ions. And so we really get the H moving to here, making H3O plus ClO4 minus. Just know that both of them happen. All right, the next one, C6H12. What is it? Strong, weak, or non? Weak. It's a non. Why did we say weak? This is a covalent compound. Is that an acid? No. If it were an acid, I'd agree, but that's not an acid. An acid is written in a format where you have an H plus, the ionizable H goes out in front of it. So this is a covalent compound. This is a non-electrolyte, so we have no reaction to write. Potentially, this is not even going to dissolve in water, frankly, but if it did dissolve, it would just be surrounded by water, staying as a whole covalent compound. All right, lithium hydroxide. Strong electrolyte. Why? It's a group 1 hydroxide. It's a strong base. All right, so we have lithium hydroxide. It's going to 100% dissociate to what two ions? Lithium plus OH minus. This is where we get to a level in chemistry where if you don't give me those charges on those ions, you're not getting credit. It's not just lithium. It's the lithium plus 1, okay? So be sure to pay attention to your charges. All right, ammonia, what is that? It's a weak electrolyte because it is a weak what? A weak base. So ammonia, you actually have to add it to water for it to have its, because ammonia is a gas normally, and so when you bubble it through water, it reacts with the water, and the water becomes basic. So in a case with ammonia, we have to add it to water, but it's weak, right? So because it's weak, this is going to be an equilibrium reaction. It's not all going to break up. It's going to go back and forth and back and forth and back and forth. That's what makes it a weak electrolyte. Bases are proton acceptors, so we're going to make ammonium and OH minus. This is what makes ammonia basic in water, is the fact we produce that when it reacts with the water. Okay? All right. NaCl. Strong electrolyte. Why? It's a salt, but more importantly, it's what kind of salt? It's a soluble salt. That's the key. You're going to learn solubility rules tomorrow, and I'll give you some tricks to remember them, like the Big Daddy rule. Big Daddy's down here. So he has a rule for solubility. All of these pictures have a story to them, and at the end of the year, you'll know all of them. So sodium chloride, we know it's a soluble salt just from, even if you don't know the Big Daddy rule, group 1 metal ions are always soluble. You have real life experience, and you know that this particular salt, which is table salt, sodium chloride, does dissolve in water 100%, so we have an arrow going that way. All right. What's this acid called? Acetic acid. Acetic acid it's a weak electrolyte. Why? Because it's a carbon-containing or weak acid. So it does dissociate somewhat in water, but what do we have to include in that dissociation equation? Yeah, our double arrows, because it's weak. Only a little bit goes, so it goes back and forth and back and forth. All right, and the last one, ammonium chloride. This is going to be a rule you're going to learn. Ammonium NH4 plus as an ion in salts, it's part of the Big Daddy rule, are always soluble. Okay, so this is considered a strong electrolyte because this is a soluble salt. All ionic compounds are salts. So anytime I say salt, it's the same thing as me saying ionic compound. So what two ions does this thing dissociate into? 100%. I need charges. I don't know what NH4 is. Thank you. Plus Cl minus. Okay? All right. So we'll get more into the electrolyte stuff tomorrow. But in order for you to be successful in AP, you have to be able to make solutions. So making solutions is going to be a little more, we're going to have higher expectations than we did with you in the past. You've done molarity calculations. You knew that molarity, what's the formula? Can you be more specific? Moles of what per liter of what? Solute per liter of? No. Solution, the full solution. Okay, there's a subtle difference in that, but we're going to make it even more clear why that difference is important, because you guys are going to have to know how to make solutions. So knowing it's solution and not solvent changes how you make them. Let's just really quick go ahead and solve for these 4 different molarities of possibilities. And you don't need your calculator for this first one. If we have 0.875 moles of sodium chloride in 1 liter, what is my molarity? 0.875. And we're in AP now. We don't write the big M when we're asked to solve. We write moles per liter. The big M is not a unit. Just like density, big D is not a unit. What's the unit on density? Grams per mil or grams per liter or whatever however they're measuring. Okay, so I need to see units. This next molarity is the same number of moles divided by, we're going to go into 500 mils. Now I'm hoping we're at the point where we can convert that in our head to liters. Can we do that? What is that? 0.5. We divide by 1,000. So 0.5 liters comes out to be 1.75 moles per liter. All right, this next one, we're going to divide it by 100 mils, which is how many liters? 0.1. Now, if you have trouble doing that conversion, then you need to go to the side and do that conversion on paper. If you mess this up, if it's at all confusing, go to the side of the paper and do your conversion with dimensional analysis. All right, the last one, we're going to dilute it a lot. We're going to take that many moles and we're going to put them in 6 liters, and that comes out to be 0.146 moles per liter. Okay, so how do we make solutions? I have a slew of little volumetrics here in this picture, as well as some on my desk. Volumetrics are very accurate instruments. They're more accurate. They're expensive because they're made specifically to contain one volume and only one volume. And they're way more accurate than any graduated cylinder that you can find. The accuracy is pretty darn close to like a burette level of accuracy. So when you're using these, be careful with them because they're not cheap. Like this little 50 mil one runs in the $20 range. Okay, they're not cheap. So the common volumes we usually have, we have 2-liter volumetrics, 1-liter volumetrics. This one right here is a 500 mil volumetric. We have a 250 mil volumetric. We have a 100 mil volumetric, and then we have this little 50 guy. So these sizes of volumetric basically dictate the amount that I make. So if I calculate, oh, for all my chemistry AP classes, I need 1.75 liters of solution, I'm going to use the 2-liter volumetric and just make 2 liters because I'm not going to be able to make 1.75 very accurately because I don't have a 1.75 molar flask. All right? So when you're given problems where we say, how do you make things, you can assume that we have that size volumetric flask. Okay? So let's pretend I'm making a solution, and I do the calculations, and I find out that I need to dissolve 5 grams of my solute, and I need to have a liter of solution. So what I do, I would take my liter volumetric, I would put my 5 grams directly in this flask, and I would fill it up. Each of these volumetrics only have one line on them. I would fill it up to the line with water. Then what do you think I need to do to finish making my solution? Stir it. So what I would do, I actually stopper it, and I invert to mix. Okay? That's how you make a solution. It's different then, and this is where students mess up. Students will say, put 5 grams in a beaker and add 1,000 mils of water. That's different, and that's wrong. Why is that different? It could be more water than I'm adding. If I put solid in here first, am I still adding to this line? Is that exactly 1,000 mils I'm adding? Probably not. That solid is going to take up, albeit it's not a ton of volume, it's still some volume. So I'm really not adding your solutions. When you mix 2 liquids, when you mix a liquid and solid, it's not an additive kind of situation. You have to utilize your full solution volume in order to do things like that. Okay? So let's go ahead and do this first one, this first problem. We're going to do 2 problems, and they're different. I'm going to describe to you how I expect, these are on the test, how to make up solutions. How would you prepare 500 mils of a 0.05 molar copper 2 nitrate solution? Now, I'm going to go into my stockroom. I'm going to pull off the shelf copper 2 nitrate. It's an ionic solid. I'm going to shake it, break it up. It's going to make some noise. what do I need to know about copper 2 nitrate to make the solution? What do I need to calculate? No, they're telling me I'm making 500 mils of a 0.05 molar. Yeah, how much I would need and what unit? In grams. I don't have a mole balance, right? I know that molarity is equal to moles per liter, right? I need to figure out how many moles I need, but I don't have a mole balance. I'm going to have to actually convert those moles to grams. Once I figure out grams, then I'm going to weigh that number of grams out and go from there. So first part of all of these problems is to do a calculation. Now, if you want to go step by step and use this and put in molarity and put in liters, solve for moles, and then convert moles to grams in a separate step, you can. Go for it. I'm lazy. I like to do one long dimensional analysis. Okay, so that's how I'm going to do it. Feel free to do it differently if you want. So what I'm going to do is I'm going to start with, I know molarity is actually moles per liter, and that's a more complex unit. I'm going to hold off on that. I'm going to start with my 500 mils. What do you think I need to convert those mils to? Liters. So for every 1 liter, I have 1,000 mils. So now what I can do is I can take my molarity and I can put that into my dimensional analysis to convert to moles. So it's 0.0050 moles per liter. That's what molarity is defined as, right? Now this is one thing people get afraid of. My liters have canceled, my mils have canceled. Right now, if I stop, I'm only getting to moles. But I need moles per liter. How many liters do I need? Oh, I do have moles per liter. Oh, I want to get to grams. Ugh. Sorry, back it up. I'm in moles of copper 2 nitrate. So now I need to figure out how many grams I have to weigh. How do I do that? For every 1 mole of copper 2 nitrate, I need 186.67 grams. All right, so I took my milliliters and my molarity to find moles. That was the first 3 blocks. And then moles to grams is my last block. And so to make up this solution, I would need 0.469 grams of copper 2 nitrate. How do you feel about that, okay? So the next step would be to explain. This is all you did in pre-AP. That's as far as you went, right? Now you have to go and say, all right, I'm now going to take 0.469 grams of copper 2 nitrate, or weigh, I can say mass. I really don't care exactly what you say, and place in what am I going to put them in? What kind? A 500 milliliter volumetric. I expect to see that because that's important. You're not going to put it in the 2 liter. There's all those to pick from. In a 500 mil volumetric, and I'm going to do what? Where am I going to fill it to? Fill to the 500 milliliter mark. If you say it's a 500 milliliter flask, I will be okay with you saying fill to the line, because there's only one line on volumetrics. Fill to the line with water. You're going to stopper it, and then you're going to invert to mix. Another way to say fill to the line, you can just use the letters QS. I'm going to QS to the line, or I'm going to QS. That means quantity sufficient, QS. It actually has a Latin-based root that you can look up. If you speak Latin, it might be interesting for you to go see. I don't even know. I don't care. I know what QS means. So you can say put the solid in, a certain amount of solid into a 500 ml flask, QS it, invert to stopper and mix. You can use that terminology and I'll be okay with it. All right, is that doable? All right, number 4. calculate the volume of 0.5 molar copper 2 nitrate needed to prepare 250 mils of 0.04 molar solution. So we're going from this to this. I need to know what's the difference in this kind of problem. How is this different than what we just did? Physically. 2 molarities. What does that mean? We're mixing solutions? Am I mixing? That's the word I was looking for. This is a dilution from what we call a stock solution. So like in our cabinets in the storeroom, we've got really concentrated HCl, like 12 molar HCl. We never use 12 molar HCl here. We use 1 molar, 0.1 molar, 2 molar, 4 molar. There's no HCl solid in existence, so we have to use the solution that we have and dilute it. So that's what this is. This is a dilution problem. What's the dilution formula? M1V1 equals M2V2. So this is a proportion. These volumes do not have to be in liters. As long as whatever you put in as the volume unit, you get out on the other side. I actually prefer doing these with milliliters because I can measure milliliters. If I use liters and get 1.36 liters, I'm like, I can't measure that. That's 1,360 mils. I can do that. So I'm going to actually probably just more often than not put milliliters in. So the way you do it, this is our stock right here, and we're diluting it to make 250 mils of something less concentrated. So I'm going to start with my stock. My stock is 0.5 molar. The question is, calculate the volume of the 0.5 molar. That's my unknown. Is equal to stock needed to prepare a 250 milliliter solution of 0.04 molarity. So my whole solution is going to be 250 mils in volume. So doing the math here, I have 2 sig figs based on that 250. So it's going to be 20 mils of this 0.5 molar solution that I have to do. So how would I make that? I'm going to take 20 mils, 20 mils of 0.5 molar CuNO32, and what am I going to do with it? What were you going to say, Emily? Dilute it with what? I was thinking she was going to say add 230 mils of water to it. Can't do that. Okay, well, I was hoping you would because I wanted that to be a wrong example of what commonly people do. You can't subtract volumes like that. You do the same thing we talked about. I don't have a 250 mil volumetric sitting here. This is a 500. Pretend it's 250. You would put your 20 mils in here and then fill it up to the line with water, stopper, and invert. Take 20 mils of the 2.5 and place. You're probably going to pipette them when you're doing them. You have these big pipettes that kind of look like miniature graduated cylinders, and you're going to suck up 20 mils, move it, drop it into your volumetric flask, and pipette into the volumetric into a 250 milliliter volumetric flask, QS with water, or fill to the line with water, stopper, invert to mix. I know you guys in pre-AP did make one solution that it was colored, right, and they put it in the spec 20. They put in the colorimeter to check if you made your solution right. Yeah, that's what we're going to be doing a lot of. All right, last problem is determine the molarity of total ions in a solution prepared by dissolving 9.82 grams of copper 2 chloride in enough water to make 600 mils of solution. What is the molarity of the chloride ions? So before we can figure out molarity of ions, what molarity should we figure out first? Yeah, just the molarity of copper 2 chloride. So let's go ahead and start setting that up. We're starting with 9.82 grams of copper 2 chloride, right? So if I want to convert to molarity, before I even deal with volume, what I got to change those grams to? Moles. So for every 1 mole of copper 2 chloride, I have 136.45 grams of copper 2 chloride. All right. Now if I want to get molarity, molarity is moles per what? Liter. So I can just do 0.6 liters down here. That's 600 mils, right? Everybody with me so far? All right. That is my molarity, moles per liter. Do I want my molarity of just the copper 2 chloride, though? No. I want molarity of the total ions. That's what the question's asking for, total ions. This sounds scary, but it's really easy. Because for every 1 mole of CuCl2, how many moles of ions do I have? 2? No, it's total ions first, and then chloride ions is later. Yes. How many ions, how many moles of ions do I have for every 1 mole of copper 2 chloride? 1, 2. Do y'all get that? You're looking at me like I'm literally from space. No, it's eventually determine the molarity of total ions is first, and then chloride ions. All right, so how many total ions do we have? Oh my God. 3. Does everyone get that? This is not the Da Vinci Code. 3 moles of ions for every 1 mole. So this is going to give me, my units will be moles of ions per liter, which is what the first question is asking me for. When you calculate that, you should get 0.360, right? Okay, cool. Now let's do the chloride ions. All the work is the same up to this point, so I'm just going to add for every 1 mole of CuCl2, how many moles of chloride ions do I have? Yes, 2 moles of Cl minus. So that's 0.240 moles per liter of Cl minus. All right, so you will commonly be asked in the more advanced problems, find the number of moles of nitrate ions. Don't freak out. Find the molarity of your thing first, and then however many nitrates are in that substance. Okay, it's a very common thing that will show up. Okay, that is all. All the home viewers, have a great day.